theory with UV Lagrangian. Integral, let's say I'll call it QI bar and e to the power minus b. This is d4 theta. This is also d4 theta. And then there's d2 theta w alpha plus hc. Okay. Later on, we may deform this theory by adding some superpotentials. In particular, we may at some point, or we will at some point, deform the theory to add plus d2 theta mij qi qj tilde. Okay. Plus summation conjugate. Plus. Okay, so this is a basic theory, and sometimes we will deform it to add a mass. Okay. So let us remind ourselves what all these fields are. Qi and qi tilde are chiral superfields. Qi transforms in the fundamental of SUN. Qi tilde transforms in the anti-fundamental of SUN. W alpha is the supermultiplet, the field strength supermultiplet of the SUN gauge field. And W alpha, that D2 theta W alpha captures the F square term as well as the kinetic term for the gluinos. Okay, is this the model we're studying? Is that clear? Louder.
E to the minus W and e to the minus W.
No, these are both e to the minus v's. In the appropriate representations. Okay, so one will be in the fundamental representation, the other will be in the anti-fundamental representation. Okay, and of course fundamental representation and anti-fundamental representation are related as being, complex conjugates. Okay, so the T matrices from the two sides are related by being minus transpose. The generator matrices. This we will use somewhere, so I'll just remind you of it. If you have the fundamental matrix U transforms under U, then the anti-fundamental matrix transforms under U dagger, but U dagger, but with a transpose, so that the indices contract with each other, right? So let's remember that if Qi is a fundamental and Q tilde I is an anti-fundamental, then this is an invariant. Okay, so if Q transforms like UQ, this guy transforms like Q dagger U inverse or U transpose, but from the right. Okay, so Q tilde transforms like U inverse transpose or U dagger transpose. U star, exactly. Okay, and then if we write U as equal to e to the power it, okay, then what we will get here is U star is equal to e to the power minus it star. Okay, and we'll use this at some point in our discussion. So Q and Q tilde transform in related but different representations. Okay, one is fundamental, one is anti-fundamental. Okay, so now there are various things that we wish to understand about this theory. First, classically, before studying it quantum mechanically. Okay, the first thing we want to understand classically about this theory is what its symmetries are. Okay, so symmetries.
Sorry, if it's Mij, Qi, Qj,
Yes.
all these are independent data?
Mij is an arbitrary matrix. You can diagonalize it. You can diagonalize it, but at the moment it's as easy to deal with. In fact, you will see for formal purposes, it's easier to think of M as a matrix than working in a particular basis where you diagonalize it. Okay?
But
you can, and sometimes we will diagonalize it. Okay? Yeah. Okay. But, yeah, good. So now we're going to study the symmetries of the theory, first setting the Mij term to 0. Okay? So question, what kind of transformations are transformations on the Lagrangian, transformation on fields that leave the Lagrangian unchanged? Now, the first thing you see about this theory is that the Q's and Q tildes do not directly talk to each other. They talk to each other only through the gauge fields, right? This is in the case that the Mij is 0. Okay? So, if we can do some transformation on Q's, we can also do some transformation on Q tildes, and these two things don't talk to each other. Next thing, what kind of transformation, and I forgot to say, I was a flavor index. I was equal to 1 up to NF, with the NF such fields. Okay? So, first thing we're going to, what kind of field redefinitions can we do that are not gauge symmetries? Okay, field redefinitions that are not gauge symmetries on this Lagrangian that will leave it unchanged. So these are global symmetries. Perfect. Or UNF times UNF if we're being classical. Okay? So Diksha tells us, okay, suppose I take Qi and I send it to, let's call it Vij Qj, where V is some UNF matrix. Then because it's contracting with Q bar from the left, okay, this will obviously be invariant because A star contracted is left invariant by unitary transformations for the usual reasons, right? Right, because you get a star and then you've got, you're doing the other way around. So you've got a dagger and U dagger U is equal to 1. Just the usual things.
This Ij indices doesn't mix with the e to the power v.
No, the e to the power v is purely in color space.
Yeah, exactly.
Ij is flavor space. So I'm not writing the color indices. Color indices are implicit in this expression. Flavor indices are written.
So then anything can pass. This Vij can pass.
This Vij just passes. It's a completely gauge invariant thing.
When you say that they don't talk to each other, this transform.
Wait, I'm saying that this thing and the thing with Q tilde will not talk to each other.
That is true.
Okay? So in addition, we can move the Qi's with a V tilde
I see.
independently. There's no relationship. Okay? So you see that the global symmetries of this theory obviously have a UNF times UNF. So far classical. We'll worry about quantum mechanically in a bit. Okay. In addition to these, okay, in addition to these, there is the symmetry that does the following. Take W alpha to e to the power I theta W alpha and takes theta to e to the, let's not call it theta, zeta, phi. Okay, some constant parameter. Okay, e to the power I phi theta, but takes theta bar to e to the power minus I phi theta bar. Okay, this I'm claiming is an obvious symmetry of the theory. First, what does the symmetry mean? What the symmetry means, of course, is that there is a transformation of all fields, a transformation of all fields that multiply the theta. Okay, so if I have a field that I say it this way, but of course theta is just something, it's not there in the final Lagrangian, right? You can write it out in terms of components. But suppose I've got a field which is A, which is equal to A plus theta B. If theta is going to theta times e to the power I alpha, I'll absorb that into B going to that time. So this is just a way of saying it. What it means it's a bunch of transformation rules for various fields. Is this clear?
So this is like W prime of theta is related to W of e to the I prime.
Exactly. So I will put, so really my W prime will be equal to W e to the power I phi W of e to the power I phi theta. And if there's a theta bar, my e to the power minus I phi theta bar.
So this is like space-time.
You can call it a space-time symmetry, but all it does in the end is transform all the various fields. Right?
Is this related to R symmetry?
This is the R symmetry. Okay? Excellent. So as Diksha said, this thing has a name, it's called R symmetry. Now first let's understand why it's a symmetry. Okay? First let's understand why it's a symmetry. Okay? It's a symmetry because each of the terms in the Lagrangian is invariant under the symmetry. Why are the first two terms invariant? The first two terms are invariant because there's d2 theta and d2 theta bar. And these cancel against each other. Remember, d2 theta is just two derivatives with respect to theta. So each of them will now pull out extra phases, but the two derivatives with respect to theta bar pull out extra phases as well, compensating. Is this clear? Okay, so that's one, these two terms are invariant. Now what about the d2 theta WW? Okay, remember d2 theta despite appearance is just two derivatives with respect to theta. So it transforms like 1 over theta. But the W is transformed like thetas. So that term is also invariant. Okay, so if we do this operation and then we just keep our wits about us and see what this operation means at the level of fields, this is another symmetry. Now, this is a symmetry that does not commute with supersymmetry. Right? Because the supersymmetry operator is d by d theta plus something. Since theta is charged under the symmetry, d by d theta is charged under the symmetry. So, in appropriate conventions, the supersymmetry operator has either charge 1 or minus 1 under the symmetry. On the other hand, the UNF times UNF acted on supermultiplets as a whole and had no play with the supersymmetry operator. Did nothing to d by d theta. Okay? So the supercharge is charged under this new symmetry, but not under this UNF times UNF symmetry. The supercharges. Q have charge either plus 1 or minus 1 depending on our conventions, and Q bar will have the opposite charge under the R symmetry, and the others leave the supersymmetry neutral. So this R symmetry is special because it's a global symmetry that does not commute with supersymmetry. Okay? In fact, that's what the definition of R symmetry is. Different people use slightly different conventions, but one way of saying it is the following. Any symmetry under which the gluino has charge 1 is an R symmetry. This is our convention here because you remember W alpha starts with lambda alpha. So the charge of W is the same as charge of lambda because there's no theta involved in that lambda. Is this clear? Okay, so W alpha started with lambda alpha, and so we get that this W alpha, the charge of W alpha is the same as the charge of lambda alpha. Okay, all good? Theta is an integration variable.
You can always keep this theta as theta but change the field.
That's what we mean by this transformation. Okay, so
How do we see that
okay, so how do we see that the because it's a dummy variable, we can do a change of variables. As theta goes to theta times e to the power I phi. And if I change w in this way and do that change of variables, the Lagrangian is left constant. But if I do that change of variables, my fields have transformed. So what I mean by this theta goes to theta going to I phi is induce the changes on the fields that come from such a variable change. This is what it means. But just to see that the action is invariant under it, it's convenient to absorb that change of fields into a change of theta.
Yes, but then when you argued that supersymmetry generators are charged, you use that theta goes to theta.
Yes, but that's another way of saying it, is that two components that are related by supersymmetry will carry different charges. It's the same argument, right? Because let's say supersymmetry is del by del theta. So it tells you that supersymmetry acting on a fermion is equal to a boson. But because the fermion came multiplied by theta, under the theta goes to theta times whatever, it would carry a different charge from the boson. Therefore the supersymmetry will be charged under it. Right? It's the same argument. It's like an active versus passive kind of thing. Okay? We will see in a little more detail as we go along. Go on, Takshu.
This W was capital D theta bar, and d theta of V.
Was d theta bar, correct. D theta bar, d theta of
So
V.
basically if we don't change V and say that theta.
Perfect. This is actually what I was going to say next. The question that Takshu is asking is how does V change under this R symmetry? I've said how W has changed, but W was built out of V. Now W was d bar d of V. Okay, so this guy now have I got it ulta? Just a minute.
It's like 1 over theta.
Yeah. Just a minute. Perfect. W should transform. It's right. Because d of theta, let's say that this is W is charge plus 1. So d transforms like charge minus 1 because theta has plus 1. So d has charge minus 1. D bar has charge plus 1. So these three carry charge plus 1. So the way this is going to get charge plus 1 is if V carries charge 0. Okay? So what I said is equivalent to saying V carries charge 0. Okay? Now V carries charge 0 and the first component of V was V mu, which is the actual gauge field. So under R symmetry, the gauge field and the actual field strength, therefore the actual field strength is uncharged. So gluino carries charge 1, actual gauge field and actual field strength is uncharged. Okay? And under the R symmetry that I've defined here, okay, under the R symmetry that I've defined here, the scalars are also uncharged. Okay? We will come back to modified definitions of R symmetry when we study anomalies later in this lecture. Okay, but under the symmetry that I've just defined here, okay, the sort of naive R symmetry, okay, we have scalars being uncharged. Okay, one last exercise of this sort. Remember that our expansion of W alpha carried a term which was theta alpha, theta beta, theta bar, sigma mu, V mu. You remember that when we expanded W in fields, there was a term which was cubic in thetas that came with a V mu. Okay? And now let's see how this goes. Okay, so the way this goes, one way of thinking about charges goes as follows. This guy carries charge 1. Okay, and we are assigning theta charge 1. Okay, so this must carry charge 0 in order that theta squared times theta bar carries charge 1. Is this clear? Now the way of saying it is we transform W, we transform all the thetas, okay, and then whatever transformation is left over from left hand side and right hand side has to be absorbed by the transformation of V. In this case, there's nothing left. Is this clear? Sunil, is this clear about the thetas? Okay, fine. Okay, excellent. So now we've got these symmetries. So let's summarize. The classical symmetries, classical global symmetries of our theory are UNF times UNF times U1R. Okay, this I emphasize is the naive U1R. Okay, we will soon correct it in a little bit. Okay, excellent.
This lambda will be charged under.
Lambda will be charged. Lambda was what? Lambda is the gaugino? Yeah, lambda is charged 1 under R symmetry. Because one way of saying that is that lambda is the first term in W. Okay, and so lambda carries the same charge as W. Yeah, so gaugino is always a charge, and in fact, in my conventions, gauginos will always carry charge 1 under R symmetry. That's how I'm defining it. Okay, that's the same thing as theta carries charge 1, because d2 theta W alpha squared has to be neutral. So lambda always carries charge 1. Okay, all clear. Excellent. Okay, now let us write down the charges of all fields in the theory, the charges of all fields in the theory under these various symmetries. Okay, so the first thing I'm going to do is to list all fields. So there is the fields phi and their fermions. There are the fields phi tilde and their fermions. I'm not listing the bars because they obviously have opposite charges. Okay, and then there are the fields, let's say V mu, and then there's lambda alpha. Okay, now on this side we'll write down all the, there's SU N F, let's call this left, and then there's U1, let's call this left, there's SU N F, let's call this right, and there's U1, let's call this right. Then we'll call, let's not mix up these guys act on the Q's and these guys act on the Q bars. Then there's U1, we'll call it R. Okay, and that's it. That's the bunch of symmetries we have. I've broken up the UNF into SUNF times U1 for reasons that will become clear. Okay, so let's fill out this. This is an easy job, but let's do it. This guy under SUNF transforms into fundamental. Okay, under U1 carries charge 1. Under SUNF here is neutral and carries charge 0. And under the baryon charge under the R charge carries charge 0. That's clear? Okay, now let us remember that phi was equal to theta psi. Okay, theta carries charge 1, so psi has to carry charge -1 under R symmetry because phi carries charge 0. Okay, and so under this everything here is the same because these commute with supersymmetry. So fundamental 1-0, but this guy carries charge -1. Clear? Okay. Similarly, if we look at phi tilde, this is -0, fundamental 1 and 0 dash 0 fundamental 1 and charge minus 1. Okay? And if we look at V mu, this is a very simple field. It's just dash, 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 dash. Carries no charge under anything. This, of course, is good. That's why you could write e to the power v upstairs. Okay? Or you can get minimal coupling, linear in V with fermions or scalars because it carries no charge. Okay? And what about lambda? Well, clearly it's dash, 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 dash here. Dash and 0 are the same. But this carries charge 1 under R symmetry. Okay. Later we will add theta to this. What theta is, I'll tell you, and we will see why. But we will do that only once we look at quantum mechanics and anomalies. Okay. All good? Excellent.
You said mu has charge 0 under U1
Yes.
You didn't wrote it.
I wrote dash. Dash and 0 are isomorphics. I write dash for singlet under a non-abelian group and 0 under abelian, so now I should change this. Okay, just sounds odd to say 0 for a non-abelian. It's identity representation. Okay, fine. All good? Excellent. So were we classical physicists, this would be our symmetry group. Okay. Now let's pretend we were classical physicists for just a minute. Okay. Let's pretend we were classical physicists for just a minute and ask, okay, suppose there's some. Okay, by pretend we were classical physicists, what I mean is let's ignore anomalies for a moment. Okay, let's ignore anomalies. Suppose there were no anomalies in the world. Okay, we could ask the following question. We could ask, suppose we look at the low energy effective, the 1pi quantum effective superpotential of this theory. What form could it possibly take? Okay, we're starting with a theory with superpotential 0. The m's are 0. We're starting with such a theory. Okay, and now we're asking, suppose quantum dynamics were to induce a superpotential in the 1pi effective action. The 1pi effective action can also be written as supersymmetric, written in terms of integrals over superspace and so on. We don't know what strange dynamics happens between the weak coupling in the UV and the strong coupling in the IR. Okay? But whatever that is, what does symmetries tell us about what form this quantum effective action could possibly take? So let's ask this question. What?
It will break first.
No, we're demanding that symmetries are preserved. Okay, it could be that it spontaneously breaks symmetry, but that has to come about from the quantum effective action. Quantum effective action has to be symmetrical. Could be its vacuum is not symmetrical. So right now we're not analyzing vacuum. Just ask what form can this effective action take. Okay, so great. So let's see. We are writing d2 theta. Our superpotentials of the form d2 theta times some function of chiral fields. What are the chiral fields in the problem? Well, there's q and q tilde. Now, our chiral fields transform like singlets. Okay? Our chiral fields transform like singlets under the R symmetry. Okay, d2 theta picks up some phase under the R symmetry. So if there were no anomalies in the theory, immediately we conclude that no matter what function we make of phi and phi tilde, if we integrate over d2 theta, it will never preserve our symmetry. And so, ignoring anomalies, we've come up with a fantastic theorem. The theorem is, as long as our Lagrange, our action is such that it preserves all symmetries, our regulator is such that we're able to preserve all symmetries, supersymmetry and global symmetries together, okay, we've proved that there can be no quantum effective superpotential. So the classical superpotential, which is 0, is also the quantum superpotential. What a remarkable theorem, right? Of course, it's not true, but still remarkable. Mm-hmm. Okay? Is the argument clear? The argument is that if quantum dynamics generates a superpotential, under the assumption that it preserves all classical symmetries, this is of course the assumption that will fail because of anomalies. Okay? But under the assumption that it preserves also classical symmetries, this has to be some function of phi and phi tilde. Now, we want all symmetries to be preserved, and we'll have some job going through the various list of symmetries and so on. But already looking at just one of the symmetries, we see immediately that no phi will obey this. Okay? And that symmetry is R symmetry. Because phi and phi tilde are both uncharged under the R symmetry. But theta is not. So no function of phi and phi tilde times d2 theta will be uncharged under R symmetry. Hence the superpotential must be 0. Okay? You see how powerful symmetries are in constraining possibilities. Now, why was this so powerful? It was so powerful because of holomorphicity. Because we were only allowing functions of phi and not phi bar. And also because we're preserving supersymmetry. We're not allowing you. See, for instance, if I just wanted to write out of components, I wanted to write something that was R symmetry invariant, it's very easy. Any function of phi, for instance, is R symmetry invariant. Any function of phi tilde is R symmetry invariant. A function of this psi times its complex conjugate is R symmetry invariant. So, in the absence of supersymmetry, there would have been no issue. It would have been easy to write down. Easy to write down things that were R symmetry invariant. Also, in the absence of holomorphicity, there would have been no issue, because had it been that we were trying to constrain a term that was d4 theta, then the transformation under R symmetry of d4 theta is 0. So any function of phi, this argument just fails. Two things play a role. A, we're preserving supersymmetry. B, there are certain terms in the supersymmetric action that are holomorphic. There are functions only of phi and not phi bar. These are terms which are integrals over half of superspace. These terms are remarkably constrained by symmetries in a way that has no analog in non-supersymmetric theories. Symmetries, I give you a field of charge 1. I can always take that field and its complex conjugate, that has charge 0. Any function of that is charge 0. Symmetries under U1 symmetry don't constrain possible corrections to actions or potentials at all in normal theories. But because of supersymmetry, because of holomorphicity, this integral over half of superspace, symmetry becomes suddenly enormously powerful. If this symmetry condition was correct, it would have been powerful enough to argue for non-renormalization of the superpotential. Is this clear?
So holomorphicity and SUSY are almost same.
Same, except that there are other terms in the action that are d4 theta terms. Say the kinetic term. That is not constrained in the same way. the terms that are constrained are those terms that are integrals of half of superspace. Okay, so supersymmetry is just supersymmetry, but now we're looking for a supersymmetric way of writing particular terms in the action, in particular the potential, the superpotential. That is very highly constrained by symmetry. Okay, not the other terms. That's the point I wanted to make. Is this clear?
We can multiply by W alpha, but you are saying that is kinetic.
That is a kinetic term. Yes, we could do that, but that would be basically renormalizing the metric on moduli space of the gauge boson. That's not what we're interested in calculating. We're interested in calculating the renormalization of the potential of the scalar. Okay, and we'll see why in just a bit. Is this clear? So though this argument was trivial, it captures the essence of what's going to go on in a more complicated situation. Okay, it's really important to remember that supersymmetry, but really holomorphicity, gives you great power in the presence of a large amount of symmetry. The holomorphicity is key because you cannot multiply by, the bars. Okay, great. Now, the next thing we're going to do is try to correct this story. Okay, the next thing we're going to try to do is to try to correct this story. Why is the story wrong in the first place? The story is wrong in the first place because not every classical symmetry of a quantum theory is a true symmetry of the quantum theory. Okay? Sometimes you can write down symmetries that look like they're symmetries of the action, but they're not symmetries of the path integral. Okay? I'm going to remind you of that. Okay? Sometimes we have, now I'm going to use the word anomalies for this phenomenon. In modern usage, a symmetry of the classical theory, which is not a symmetry of the quantum theory, in modern language, people hesitate to call that an anomaly. They might say, this is just not a symmetry. And they reserve the term anomalies for anomalies for symmetries, the global symmetries that are genuine symmetries of the theory, that would get deformed if you coupled a background field to some other global symmetry. Okay? But I'm going to use the 1990s usage of the term anomalies. Just warning that sometimes people don't use the word in the way that they did in the 1990s. Since all the reviews in Seiberg-Witten theory will use the word anomaly for this, I'm going to use that word. But just what it means at this stage is very crude. It's just something that looks like a symmetry in the classical theory, but it's just not a symmetry. Okay? So let me remind you how that happens. Let me remind you that there is, suppose you take a current. Okay? Suppose you take a current and of some global symmetry. Could be SUNF, could be U1R, could be U1B, whatever. Okay. And in the quantum theory, if you compute del mu J mu. Okay? This is zero classically. But quantum mechanically, this can become del mu J mu, can become some number times F wedge F. Okay? Del mu J mu can become some number times F wedge F, where F is some field strength. Okay? In the current context, F is simply, this will be a trace, F is simply the field strength of the gauge boson. Okay? The classical relation del mu J mu can be modified to the quantum relation del mu J mu is equal to some number times trace F wedge F. And that number is determined by effectively the following things. Trace of TA, TB, TC, where this is the representation matrix for okay. every time we have a chiral fermion in the game, that chiral fermion contributes something to this number. Now suppose that chiral fermion transforms in some representation under the symmetry under consideration, and some other representation under the gauge field, the gauge group. Okay? In this case, these two are the representation matrices of the chiral fermion for the gauge field, whereas this guy is the representation matrix for the chiral fermion under the symmetry that we are studying. Is this clear? So imagine that you make a list of all chiral fermions in the theory. Okay, you take your chiral fermion and make a big column of it. Okay, now these chiral fermions, they transform in some representation of the gauge field and some representation of all the other symmetries. Okay, so for each chiral fermion, you are supposed to compute this quantity, sum it all up over all chiral fermions, and that gives you the coefficient of the anomaly. First, is the statement clear? Second, is it familiar? First question, is the statement clear?
Yes.
Okay, so for instance, suppose we were doing SUNF. Then this thing, okay, this thing here would be the representation matrix for SUNF. Okay, now the chiral fermion would transform in a tensor product of the representations of SUNF and gauge group. So that TI matrix would be identity in the gauge sector, and whatever it is in the flavor symmetry sector. Okay, and similarly the gauge matrices would be whatever they are in the gauge sector and identity in the flavor sector. And then we are supposed to compute all of that and compute some trace. Okay, and when we do that, we will get some number which is then associated with the coefficient of this anomaly. Okay, so in this case, these two indices will be contracted because here we are contracting them, and this index alpha will be the index alpha of the current here. J alpha. Okay, is this clear?
So whatever symmetry is being broken is the one that
is on the first T, and those two in this situation are the gauge fields. Now, as I've said, there is a more modern usage of anomaly where you could put other global symmetries into TA and TB. We're not worrying about that for the moment. Okay, those are genuine symmetries of the theory that would be broken had you turned on background fields for the global symmetries. We're not worrying about that. We're just worrying about what is an actual symmetry of the theory which is broken by dynamical gauge fields. Now, so first question, is it clear what I mean? Second question, is this familiar to you? All of you have seen this in some language, right? I'm not proposing to sit and derive this and so on because that will take forever. If that's okay, Weinberg has a beautiful chapter on anomalies. If you're not familiar with this, I'll ask you to look at that chapter. Okay. Green-Schwarz-Witten has a beautiful chapter on anomalies. If you want. Is this okay? Can we take this and go on? Okay, excellent. So, excellent. Now, okay. Now the first thing that we can use this for is to apply this thing to the gauge symmetry itself. Suppose T was a gauge symmetry generator. Okay? Then we get the equation that del mu j mu of the j coupling to the gauge symmetry is given by this formula. Okay? Now, What we're supposed to do is to sum this over all the chiral fermions of our theory. Okay? And we get a contribution from each fundamental chiral fermion. If that was not cancelled by an equal and opposite contribution from anti-fundamental chiral fermions, we would have got something non-zero on for the del mu j mu of the gauge theory itself, of the current coupling to the gauge symmetry. This is the reason why we are studying the theory with equal numbers of q's and q tildes. The theory with, if you had one number of q's and another number of q tildes, would have had an anomaly for the current that couples to the gauge symmetry would not have been conserved. And if you have a current coupling to a gauge symmetry that's not conserved, that's not a feature of the theory, it's a disaster. Because a theory, gauge symmetry coupling to a non-conserved current makes no sense. Okay? So if you try to quantum mechanically define a theory with one number of q's and another number of q tildes, you will get a theory that just makes no sense. Okay? There are three chiral fermions in the game. There are the partners of q, the partners of q tilde, and the lambdas. The lambda contribution is 0 because that's an adjoint, because it's sort of complex conjugate to itself. The fundamentals give you some contribution, and in our theory, the anti-fundamentals give you a compensating contribution. Okay? This is related to the thing that we talked about, that whereas the t's for the fundamental and the t's for the anti-fundamental have some star, but more importantly have that minus sign. So the three minus signs make this thing cancel. Okay? So the first thing that we should be looking for is whether our theory makes quantum mechanical sense or not. This is the question about whether the gauge anomaly itself vanishes, whether del mu j mu of the current coupling to the gauge boson is 0 or not. Okay? This is true, but would not have been true if we started with a theory of one number of q's and another number of q tildes.
So in the chiral anomaly, that I am familiar with, in that case, the non-conserved current is this axial.
That's the axial thing. That's a completely different thing. So you see, the chiral anomaly happens in QCD and QCD continues to be consistent. Okay? That is a global symmetry that would have been a global symmetry in the classical theory, but is not actually a symmetry because of this kind of effect. D mu j mu of the global current is equal to some f wedge f. Okay? But QCD is anomaly free in the sense of gauge anomaly, just because all quarks are Dirac fermions. It's chiral plus antichiral. Okay? So there are two separate things. There's the gauge anomaly, whether you're looking at a theory that makes sense. And then you can ask whether global symmetries in the theory are actual global symmetries. First we have to make sense, then we can worry about symmetries. Is this clear? So this is the reason that we study the theory with number of q's equals number of q tildes. All good. Now that we've got that, we want to look at all these global symmetries and see which of them are actually symmetries. Let's first look at the SUNFs. You see, in the SUNFs, this thing is always 0. Why is that? Because this lives in a different space from this guy. So the trace is trace on this space times trace on this space. And the trace on this space vanishes because it's an SUNF matrix. It's the generator of some SUNF field, which by definition has 0 trace. Is this clear? Okay? So, this object here is always good for the two SUNFs. Okay, next question. Okay, next question, what about the U1s? Okay, so next question, what about the U1s? Well, for the U1s, this guy is whatever it is. It just depends on the representation in which this U1 field transforms. And this guy is just a charge. Okay? So we get Q times some function of representation that one can just compute. This trace of TA. It depends on which representation we're working. Is this clear? Okay? And in some convenient normalization, this function of representation is 1 for fundamental, 1 for anti-fundamental, and 2n for adjoint. Is this clear? Okay, this is a calculation you can do. Just some group theory of representation matrices. I hope I've not messed up on the factor of 2. I hope it's not 2, 2, and n. We'll soon find out if I messed up. I think it's 1, 1, 2, n. Okay? Great. So now, with this in mind, let us try this quantity. Okay? Let us try this quantity for the sum of these two U1s. Okay? So let us take the sum of these two U1s and call that U1 baryon. Okay? And let's see how this how this thing transforms. Okay? So let's do this. Actually, fine. Why don't we do it for each U1 separately? Okay? So what we're going to do is to compute U1 from Q's, U1 from Q tildes, and U1R. And we're going to compute the contribution of the 3 chiral fermions in the game, which are psi, psi tilde, and lambda. Psi, psi tilde, and lambda. Okay, now we have all the rules written down on the board, so it's easy to do the calculation. Okay, psi is charged under this, let's not go, this is the U1 of a Q. Psi is charged with charge 1 under this U1 for Q. Okay, and psi was in the fundamental. So this gives us a 1 because it's 1 times charge. Is this clear? Is what I'm doing clear? Everyone's looking a bit. Please ask questions if it's not clear. Let me finish filling up this table and then you ask whatever questions you want. Okay. So, so you have this psi here which gives you this 1 here because it's 1 times 1. We get a 0 here because psi is uncharged under the U1 for Q tilde. And for this, we get a minus 2n because psi had charge minus 1 here and and minus, just a minus 1. We get a minus 1 because psi was in the fundamental. Good? Okay. Now, what about here? This guy is 0, this guy is 1, this guy is minus 1. That's clear. And what about here? Here, this is 0 under both because it has nothing to do with these U1s for global symmetry. But what about under this guy? Under this guy, it carries charge 1 and then there is a 2n. So we get 2n. Okay? So you see that as written, all the symmetries that we've looked at are anomalous. Right? All the symmetries that, the way the symmetry would be non-anomalous is if this this thing added up to 0. Right? The contribution from the various fermions added up to 0. So that del mu J mu would be 0. But for this U1, only this guy contributes. So it's anomalous. For this U1, only this guy contributes, so it's anomalous. For this U1, all these 3 are contribute, it's anomalous. Okay? So let's look at the total. Here we get 1, here we get 1, here we get 2 into n minus nf. Because the first ones, you're right, because there was nf and nf. Thank you. Because there were nf of them. Thank you. Absolutely right. Thank you, Diksha. Right, because there were nf different flavors, I forgot to account for that.
There is psi bar and psi tilde bar.
But they are anti-chiral. We're supposed to count only chiral fermions. That's how the rule goes. Look at all chiral fermions, make a list, and then. Okay? So that's the great thing that, in supersymmetry, the chiral fermions appear in chiral multiplets. And the complex conjugates have anti-chiral fermions. Okay, so we don't have to worry about those guys. Excellent, but excellent question. Okay, so now it looks, of course, like all three symmetries here are anomalous. But of course, that's just a matter of basis. So, let me call this the difference between these two U1s. Okay, let me give these names. I'll call these U1A, U1B, and U1R. Okay, suppose I look at not B, alpha, beta. Suppose I call U1 baryon. I define this to be U1A minus U1B. Okay, so every charge, the currents are the current for U1A minus the current for U1B. The charges are charges for U1A, a new basis in the space of U1 symmetries. Nobody can stop me. If I do that, you see that the two NFs cancel. So this guy is non-anomalous. Okay, now suppose I look at U axial, which is equal to U1A plus U1B. Okay, this guy has anomaly 2NF, anomaly coefficient 2NF. All good? Okay, so this guy carries anomaly coefficient 2NF. Okay, and if I look at the R symmetry, this guy carries anomaly coefficient 2 into n minus nf. So now suppose I define a new R symmetry. A new R symmetry, let's call it U1 R prime. I want all my R symmetries always to have charge 1 for the gauginos. So it will be equal to U1R, I won't change the coefficient of that, so that gaugino will always carry charge 1. But then I will subtract what I need to of this. So let's say minus 2NF by 2 into n minus NF. Other way around. Minus 2 into n minus nf by 2nf u1 axial. Okay, this guy is non-anomalous. By definition, because this guy, because the coefficient for this fellow is this, and the coefficient for this is, it's organized to cancel. Okay, so this is the same as, okay, now let's just call it, I won't keep writing U1. R prime is equal to, let's simplify this. So it's R minus, also plus NF minus N by NF into axial. Okay, which is equal to NFR plus A minus NA over NF. Okay, so under this symmetry, yeah, sounds good, right? Under this symmetry, my under this modified R symmetry, my theory is actually this is a genuine symmetry. Okay, so of the three U1s, one is actually anomalous, but two linear combinations are not. The two linear combinations are U1 baryon and this modified R symmetry. Now before we move on, let me check I've got this combination right. Okay, so according to Seiberg, so let us add a new column for U1 R prime, which charges under the non-anomalous symmetry. So we've sort of made it by definition that this is 1, this is of course 0, and now what about phi? Phi, according to this, carries charge NF minus N by NF, because A was charge of this plus charge of that. Right, so phi carries axial charge 1. Okay, so this is NF minus N by NF. This psi is this minus 1. So minus 1, which will become minus N by NF. Okay, phi tilde is also NF minus N by NF, and this will be minus N by NF. And let me check if this is what it gets. NF minus NC by NF for Q and Q tilde. Very good. Okay, I think we're in good shape. Okay? All good? Excellent. Okay. So, what have we discovered so far? We've discovered so far that the actual symmetries of the theory are not 3 U1s and 2 SUNs. It's 2 U1s and 2 SUNs. Right? We've made a basis for the actual symmetries, which is U1 R charge, U1 baryon, and the 2 SUNs. Okay? Now that we've got this, we're going to do more. But before we start doing that more, now that we've got this, we can now replay our earlier attempt that we tried very naively with classical symmetries. Okay? We can ask, what is the possible allowed form of the superpotential? The quantum effect of superpotential. Is the question clear? Okay, let's try to address it. Okay, so we want d2 theta, some function of phi and phi tilde. And it has to be invariant under this guy, some of these two, and this guy. Okay, let's first get the two SUNs. SUN, difference, thank you. Difference of those two, thank you. The baryon, difference of those two. Thank you. And R, yes. Okay, so it has to be invariant on the two SUNFs. Now, remember, there's another property of the superpotential that I haven't been emphasizing, but it's of course true. It has to be gauge invariant. Okay? Now, remember that phi's, I call them Q's. Q's transform in the fundamental. Q tildes transform in the anti-fundamental. Okay? So, everything gauge invariant can be built out of some functions of Qi, Qj. Okay? Where these gauge indices have been contracted, but the flavor indices are left free. Okay? Let's call this quantity Mij. Can't be a function of Q and Q tilde by itself. The gauge indices have to contract. The only thing that's available for the gauge indices to contract, well, okay. Honestly, okay, let me start. Honestly speaking, there's one more thing. I'm considering, let me specialize to the case NF less than NC. In this case, this is the only thing that you could have done. Why is that? Actually, there's one more thing you could do, which is to put n different fields together and contract with an epsilon. A baryonic kind of object you might have tried to have. Okay? But for that, you need at least n different flavors, otherwise you get 0 because you're contracting with a completely antisymmetric object. So if NF is less than NC, we don't have to worry about that. We'll come back to that in a moment. We'll come back to later value, higher values of NF and NC in a moment. Okay? Right. So everything has to be a function of these Mij's. And this function of the Mij's has to be invariant under separate multiplication of SUNF from the left and from the right. Because the I index is one of the SUNF indices and the J index is another SUNF index. Now, can you think of anything? Suppose you're going to be multiplied by U something, U dagger. Then you can make traces of that field, products of that field and take trace. But you're multiplying by U1, M, U2 dagger. Can you think of any function of this matrix that is invariant under such a transformation? Determinant, excellent. The determinant is invariant because determinant of A, B, C is determinant of A times determinant of B times determinant of C, and determinant of each of these U's is 1. Because we're talking about the SU part. Okay? And in fact, it's not hard to convince yourself that the most general such function is a function of the determinant. Okay. So already we've got a great amount of progress. This, by the way, Shubhan, is the reason it's better to think of this. Okay, this is a different M, I know. But even for the mass matrix, similar such things. Think of it as a matrix is nice. So let me go this is the meson matrix. Please distinguish it from the mass matrix we wrote on the board. We'll call mass matrix up here, we'll call little m, okay. Little m, ij, qi, qj tilde. This is the meson matrix. It's a dynamical field, a chiral superfield. Okay, I don't want to change terminology because this is what everyone uses. Fine. So everything has to be a function of det m. Now that we know it's a function of det m, the U1 baryon invariance comes free. Right? Because under U1 baryon, Q and Q tilde are transformed oppositely. So det m is invariant under U1 baryon. And therefore any function of det m is also invariant under U1 baryon. Okay? All that remains is to enforce invariance under the U1 R symmetry. R prime symmetry, the genuine U1 R symmetry. Okay? Now what are the charges of phi tilde under the U1 R prime symmetry? It's just twice of this. Right? Because each of phi and phi tilde carry the same charge. It's nf minus n divided by nf. So the charge of this, so the charge of Mij, this field, so this field carries charge 2 into Nf minus N divided by Nf under R prime. But now we have a determinant. A determinant is a product. This is an Nf cross Nf determinant. And a determinant is a product of Nf such elements. Okay? So det M carries charge, R prime charge, Nf times this. So 2 into Nf minus N. Theta carried charge 1 under this R symmetry. So d2 theta carries charge minus 2. So if we take det M to the power alpha, then we need that alpha into 2 alpha into Nf minus N plus minus 2 is equal to 0. Because d2 theta carries charge minus 2, and this is the charge of this thing. And so we conclude that alpha is equal to 1 divided by Nf minus N, or equal to minus 1 divided by N minus Nf. This is a better way of writing it because N is greater than Nf. Okay? And so we conclude that the only possible allowed form for the superpotential is d2 theta 1 over det M to the power 1 over N minus N. Isn't this remarkable? d2 theta to the power 1 over M det M into N minus Nf is the only possible for allowed form for the superpotential. Now, let me check. Perfect. Perfect. Okay. Okay. Any questions or comments about this? So you see that even though our failed attempt last time, our wrong classical attempt gave the wrong answer, it gave the right sense of the answer, correct answer. That is, symmetries are powerful enough to almost completely determine the allowed form of the superpotential. Now this result, because it follows from symmetries, we'll say more about it in a moment. But this result, because it follows from symmetries, is just totally exact. If there, it could be the coefficient of this is 0. Symmetries don't prevent that. But if the coefficient of this is non-zero, okay, then up to some number, without doing any work, we know the quantum superpotential in the theory at low energies. Isn't it amazing? Okay, now 2 things. Notice that in the case that Nf was equal to Nc, the anomaly of the naive R symmetry was already 0. So our classical argument, which in general was wrong, was correct for the case Nf equals Nc. Okay? And we see that emerging from this answer here, because in the case that Nf is equal to Nc, we get an absurd superpotential. It's really the statement that the superpotential should just vanish. There's no function of det M that gives you the correct. It's the same argument we had before. That is, there's a d2 theta, but none of the fields transform.
There is no solution to this
there's no solution to this equation. Right? So in the case that NF is equal to NC, there can be no superpotential. That was the same as the classical argument. It's just the classical argument was correct then. Okay. In the case NF is not equal to NC, the classical argument is corrected, and this is the correct version of this.
But whether NF equal to NC or not equal to NC, only one symmetry is always broken.
Only one symmetry is also always broken. But the point was that the one symmetry that remained unbroken at NF equals NC was the naive R symmetry, under which phi was uncharged, under which Q and Q tilde were uncharged. So if that is a genuine symmetry, then there's no superpotential, because d2 theta is transforms and phi Q and Q tilde don't. So it's not a question of how many are broken, it's which ones.
So the basis is actually important.
Which basis? You see, the basis is what told us what the true superpotential was. You see, the point was that under the naive R symmetry, phi and Q and Q tilde were uncharged, and therefore we could not form a superpotential. Under the true R symmetry, Q and Q tilde are charged, so we can get a superpotential, but only with a specific power. But if you go to NF equals NC, Q and Q tilde are not charged again, and so it's impossible. All good? Okay, excellent. Now, there is something about this that seems a little odd. Okay, and the thing about this that seems a little odd is that the dimensions are off. Right? We've got d2 theta. So firstly, I'm never writing it, but there's always a d for x. There's d2 theta d for x times something, so that something has to have dimension 3. Why dimension 3? Because d for x carries length dimension 4, but d2 theta carries length dimension -1, because d2 theta is like derivative with respect to theta, and each theta carries dimension half. Okay? So whatever we multiply this thing with has to have dimension 3. Okay? At the moment I don't mean some sophisticated quantum dimension. If we had a conformal field theory, we may want to talk about some sophisticated quantum dimensions. But I'm just talking about meters, kilograms, units. All formulas have to have the right units. Quantum or classical, they have to have the right units, really. Okay, I'm just talking about what people sometimes call engineering dimensions, which I always think is a sort of insult to engineers. but anyway, so fine. What is the engineering dimension of phi? Well, it starts as the phi field, so its engineering dimension is 1. Okay, so therefore the dimension of M is 2. Therefore the dimension of det M is 2NF. Okay, therefore this quantity carries dimension, mass dimension. It carries dimension 2NF minus 2NF divided by N minus NF. That's the dimension of this quantity in mass units. Is this clear? Okay, but we need plus something. We want to put a something here, whatever it is. Let's call it something. So that plus something, okay, has to be equal to 3. Okay, so the dimension of that something is equal to 3 plus 2NF by N minus NF. It's looking a bit odd. Anyway, let me get it and we'll see. 3N minus NF over N minus NF. Okay, so that something, whatever it is, should carry some perfect mass dimension 3n minus nf over n minus nf. Now, what could that something be? Any ideas? You see, it has to be something with a scale, but Liouville Lagrangian had no scale. Is that a problem? Of course, it's not a problem, because in quantum theory, sometimes scales are manufactured. This theory is not free, sorry, not conformal, nobody claims so. In fact, you can compute its beta function. It's non-zero. Okay, I'll review the result of that beta function calculation in a minute. But it's non-zero, and therefore this theory we expect. You see, remember last class I told you about the general expectations. If NF is small compared to NC, we expect confinement. NF somewhere intermediate, maybe we expect conformal behavior. NF very large, we have non-asymptotically free and free gluons. Remember, we're working in the case NF less than NC. So maybe that qualifies for the range where NF is in the confining range. Okay? Nevertheless, whether confining or not, the beta function, the one loop beta function induces a scale in the problem. In the case of QCD, we call that scale lambda QCD. Okay? We call that scale lambda QCD. Okay, so this theory here presumably has its own dynamical scale. Let's call that scale lambda. We won't add the QCD because this is not QCD, but it's a supersymmetric cousin of QCD. Okay, and so what must be happening is that this superpotential here is d4x d2 theta lambda to the power 3n minus nc by det m to the power n minus nc. I've dropped f somewhere. Hey, what am I doing? Have I mixed up my n? My n was nc and nf was nf, right? Sorry. 1 over n minus nf. People usually put c for n, nc minus nf, c for color. What? Okay. So it must be that this is the form of the superpotential where there is some as yet unknown number. Now this number, what its value is a bit, you see, lambda depends on your scheme. Lambda QCD depends on your scheme. Lambda is defined as follows, right? Lambda is the scale at which the coupling constant becomes 1. But coupling constant depends on your renormalization scheme. If you use MS bar scheme, you get one value of coupling constant. Use MS scheme, you get another value. Lambda is not an absolutely defined number. So as long as the number there is non-zero, you can basically set it to 1. The only important question is whether that number is non-zero, 0. Okay? I will give you an argument as we proceed that this number is non-zero. Okay, any questions or comments about this? This quantity here is called the Affleck-Dine-Seiberg superpotential and was discovered using sort of the arguments I gave by Affleck, Dine and Seiberg in the early 1980s, 1984, 1985, thereabouts. It took 10 years between then and going to the other stuff we'll be discussing. So they already knew at this stage that this theory has an more or less exactly computable superpotential. They didn't really know what to do with it when n was less. This is the case, n less than nc. Okay. Okay, any discussion about this? Can I go on?
When you said you wanted to construct the potential out of i's and not the size and not of the psi bars, why you
The Q's and not the Q bars, yeah.
why
Why? Because all potentials for scalar fields come from superpotentials.
yes
Superpotentials are d2 theta times function of chiral field.
yes
Would not be supersymmetric if you added an anti-chiral field.
polymorphy
It's just supersymmetry. Supersymmetry tells you that there are some terms that are supersymmetric that are integrals of half of superspace. Those terms can only be functions of chiral fields, therefore holomorphic in field space.
yes
Okay? If you add an anti-chiral field, you can do it, but you've broken supersymmetry. We want to preserve supersymmetry. So supersymmetry is there in the UV theory, presumably it's there in the IR theory.
so if you want to add d4 theta kind of term,
Then you can do it, but that will not contribute to the potential. Those are terms like the kinetic terms. Okay? So there are special terms which are related to special processes in the theory that are controlled by d2 theta terms. The remarkable thing in this theory is that the potential is one such term. The potential for phi. Okay? Okay. So we have basically computed exactly the quantum effective potential in this theory in half a class doing no calculation. Isn't it amazing? I mean, it's totally remarkable. We didn't get the answer 0, okay? It's very, when you do something exact and you get the answer 0, you can claim great satisfaction, but it's always a bit disappointing, right? 0 is not a very interesting result. We didn't get the answer 0. We got a very interesting answer. Exactly. Doing no work. It's the dream of a physicist, right? You be lazy and you get the exact answer. Hey, very non-trivial. Okay. I will tell, you're not satisfied. Huh?
this is the brute force way of deriving, right? Using symmetry.
I think he has a different idea of brute force. Okay. Yeah, there is, for the special case, NF is equal to NC minus 1. There is another way of deriving this. Okay, let me outline that for you. In fact, if one of you want to lecture on this, that would be a great guest lecture to have in that. Maybe Diksha, you're an expert in these kind of things, like instant on zero modes and so on. So maybe Diksha could at some point give us a lecture on how you can compute this using instant on calculus for NF is equal to NC minus 1. I'll give you I will give you just 2 minutes on it. You see, first, let me remind you of one or two things. You know, the coupling, if you just use one loop running of the coupling constant, okay, then e to the power minus a pi squared by g squared, this may be 16, okay, is equal to lambda to the power, the coefficient that appears in the beta function, and which in this case turns out to be 3nc minus nf. Are you familiar with this? If you take let me remind you of it. Let's take the beta function equation and integrate it. Okay, so say we have dg by d log lambda. Okay, dg by d log lambda, and let's use a convention where log lambda increases towards the IR. This is an increasing function. Okay, so this is equal to, which is probably the opposite of, okay, let's use the UV, the high energy convention. So G increases towards the IR, so decreases towards the UV. Log lambda is increasing towards the UV. So we get minus G squared times some number. Let's call that A. This is the beta function. This is the structure of the beta function of any asymptotically free non-abelian gauge theory. Okay. This A along with the right 8 pi squares is this thing here, but we'll see that. Now suppose I solve this equation. So I get dg divided by dg divided by minus ag divided by g square is equal to minus a log lambda. Let me write this as, yeah, I'm going to write this as G square. Sorry, is this G or G square? Sorry, just one.
You want 1 by G square after integration?
Yeah, just one second, The beta function. It's probably G squared and G to the 4, right? Oh, just a minute. Maybe I've got this as, I may have got this may be G rather than G square. Let me do it. I may have some square or 1 power of. Let me do it and then we'll see. Okay, so we integrate this. This is d of 1 by g is equal to minus a log lambda. Okay, then I'll take the minus to this side. And then I just, d of log, sorry, yeah. No, d of 1 by g, right? D log. Yes. Okay. And so I get that minus 1 by g up to some number, overall constant, is equal to a log lambda. And let me call that log lambda minus divided by lambda naught. So that if g is equal to whatever, this is log lambda minus some number. Okay, so then this tells me that now I exponentiate both sides. So I get e to the power minus 1 by g, and I put the right 8 pi here. 8 pi. Okay, e to the power 8 pi by g is equal to lambda to the power a. Okay, this is g of lambda. Okay, and then we make this a number dimensionless by making this lambda by lambda naught to the power a, where lambda naught is lambda QCD. Okay, and right, as g goes to infinity, well, first, if g goes to 0, when g goes to 0, we should have had lambda to infinity. Why is that not working? When I integrated, I needed a sign. Thank you. Perfect. So now when g goes to infinity, g goes to 0, we have,
Lambda goes to infinity.
yeah, lambda goes to infinity, which is correct. Okay, when lambda is equal to lambda naught, g is 8 pi. Oh no, g is this is 1, so g is infinity, exactly, g is infinity. G is infinity, right. So the lambda naught is the scale at which g goes to infinity, and fine. So this relationship we will remember. Okay, this relationship we'll remember. So notice then that if I solve for lambda naught here, okay, lambda naught to the power a is equal to lambda to the power a times e to the power minus 8 pi by g of lambda. Yeah, now I have the feeling that I should have had a g square. Maybe the I have the feeling I should have had a g square. Is the right relation d log g square by d log lambda is equal to g to the 4? Is the beta function in terms of g square? I have the feeling I should have had a g square. Okay, grant me that this is actually a g square. Okay, should actually have been a g square. Now, and maybe 8 pi should have been 16 pi. Now the reason that I put it this way is the following. This quantity is what you would get from a single instanton. You see, in Yang-Mills theory you have a 1 over g squared outside. Okay? And then instanton effects. Okay? Instanton effects a single instanton comes with some order 1 number in the action. But there's a 1 over g square. And when you organize it correctly, that order 1 number is what you have here. So this quantity here is like a 1 instanton effect. Okay? So every time you have a lambda naught to the a, it's what you would get from an effect with 1 instanton. This a is the coefficient of the beta function, which is this n minus 3nf. Okay? Now why did I tell you all of this? I told you all of this because in this language, this quantity here was lambda QCD, which was what we call lambda naught below. Okay? And this is lambda naught to the power 3 nc minus nf times some strange power. But when nc minus nf is 1, that strange power is 1. So this is exactly the factor you would get. An instant count comes with 1 over 8 pi by g squared, which when you replace it by its running value is lambda naught to the power 3 nc minus nf times some lambda power. Okay, so the lambda naught power is precisely the power you would get from a 1 instanton calculation. Okay, now the other reason that you expect instantons to be relevant here is the following. As you might know, reliable instantonic calculations in QCD are extremely difficult. Okay? Reliable instantonic calculations in QCD are extremely difficult because the QCD instanton has a scale factor. Are you familiar with this? That there are 8 collective coordinates for instanton, an SU2 instanton. Its location, that's 4. Its direction in color space, that's 3. And then 1 scale factor. How big the instanton is. When the instanton is very small, all fields are weakly coupled because of asymptotic freedom, and it's easy to control instanton effects. But you have to do an integral over the moduli space of the instanton, and the instanton can also become very large. In that region, QCD is very strongly coupled. To compute the effective determinant around the instanton, for instance, it's not good enough to use 1 loop. Okay, so actual calculations in QCD using instantons are very tricky. Okay? If your theory is genuinely QCD. However, if you've got a theory which, a gauge symmetry which is broken by a Higgs phenomenon at some scale, okay, then instantons smaller than that scale can be dealt with reliably because they're small and so asymptotic freedom helps us. And instantons larger than that scale do not exist because the gauge symmetry is broken. So in a situation where you have a broken symmetry, you can reliably do instantonic calculations. Okay, so in a situation where you have a broken symmetry, you can reliably do instantonic calculations. Okay, now this feeds into what I was going to tell you next, but let me say it in words now and we'll say it in formulas in 2 minutes. In this theory, we can ask classically, what are the vacua of this theory? And as we will see in a moment, the classical vacua of this theory are associated with giving Q and Q tilde arbitrary but equal expectation values. But there are only NFQs and Q tildes. So those arbitrary but equal expectation values can break the gauge symmetry down from UN to UN minus UNF. As long as n minus nf is 2 or larger, a non-abelian symmetry is preserved and instantonic calculations are very unreliable. On the other hand, if n minus nf is 1, no non-abelian symmetry is preserved. So the gauge symmetry is broken down to U1. In this case, it's the situation where you can reliably do an instanton calculation for the reason I mentioned. For the reason Diksha will one day tell us. Okay? And in this situation then, you can actually do a calculation. And in that situation, this has been calculated and you get exactly this structure. Okay, I'm sorry, it was a long answer to your question, but that was one microscopic mechanism for generating this thing. But you could ask, what is the microscopic mechanism when n is not equal to nf? NF minus, when NF is not equal to NC minus 1, maybe by now people have some words to say, but I don't think anyone has a calculation. What we will see as we go along is that we can, given one of these potentials, we'll be able to use logical arguments to generate all the others. So the fact that it's non-zero and calculable at NF equals NC minus 1 means it's non-zero and we know its effective value at all values of n and NC. We'll see how that goes. Okay. So, sorry, fine. Okay, excellent. Fine. So, we're almost at the end of the class, but let me just quickly start the last part. The last part of this class is this. It is to ask, what does this Affleck-Dine-Seiberg superpotential mean for this theory? Okay, so we've got the superpotential. Now we're going to ask the following question. Let's go back here maybe. Now we're going to ask the following question. So what does this mean for the vacuum structure of our theory? Okay. Okay. What does this mean for the vacuum structure of our theory? So we will answer this question in steps. First I'll give you a sort of crude answer and then we will, I'll give you a technically correct but physically crude answer, then we'll think about it a little more. Okay? The question we're going to ask is this. Now that we are able to exactly compute, we have been able to exactly compute the superpotential of our theory, we have therefore been able to exactly compute the quantum effective potential for our scalar fields. Now, the value of the scalar field in the vacuum is the one that extremizes the quantum effective potential. So I'm going to ask, what is that value? What does it equal? Okay, I think it's already clear to you from this formula that without a mass the answer is m goes to infinity. okay, because this potential is sort of decaying like this and will become 0 only at infinity. This is already clear more or less, right? But let's see it in a little more detail. The first question we're going to ask is, ignoring this potential, if we were working classically, what is the potential for the scalar field in a theory? Okay? So, if we're working classically, there's no F term, there are only D terms. And let us remember that dA was equal to phi bar Ta phi summed over all the chiral fields in the theory. Right? Do you remember this from last time? Okay. Okay. Now, in our problem, how many chiral fields are there? There are the Q's and the Q tildes. Okay. So dA is going to be equal to Qi Ta Qi bar Ta Qi sum over I, okay, plus sum over I Q tilde I T star A, okay, Q tilde bar I. And with the minus sign, because the generators were minus Q T star, because we took U to be e to the power IT. Okay, so we got minus T star. Okay. So the full potential is sum over I Q bar I Ta Qi minus Q tilde I Ta Qi, and then the whole thing square. Okay. Now we want to find, the question we're going to ask is the following. Okay, question we're going to ask is, given 2n, given the 2n, there are these, each of these Q's is an NF times NC matrix. NC is color, NF is flavor, and each of the Q tildes is also an NF times NC matrix. Okay? Question: if you are able to, so we're going to ask the following question: how many supersymmetric minima does this have? Supersymmetric minimum is one in which this quantity is 0. Only way you can get this dA squared to be 0, sum over all A, is each dA is 0. Okay? So how many supersymmetric minima do we have? How many minima do we have in which this quantity vanishes for all A? Vanishes as a matrix. Or vanishes little a by little a. Yeah, vanishes little a by little a for all A. Okay? Now, if you find one one place where this happens, then clearly by acting on with a gauge transformation, it will continue to vanish. Or if you find one value, but clearly by acting on it with global UNF times UNF symmetry, it will continue to vanish. Okay? So what we're searching for really is the set of all such configurations. Okay? The set of all such configurations on which this thing vanishes modulo gauge and global symmetries. Once we have that, we have everything. Just as a simple classical question. Okay? So let me leave this, let's stop this class by leaving this thing to you as an exercise. Okay? As a simple classical question, try to find the set of all configurations. Remember that NF is less than NC. Find the set of all configurations in which these things just completely exactly vanish. Okay? And next class we will come back to using that to analyze the vacuum structure of our theory. Okay, end of class. Any questions, comments? Any other discussion? Let me tell you where we are. Okay, first questions or comments?
The square means
sum over A. Yes. So dA squared sum over A. What we're supposed to do is to square dA and then sum over all A. So it's a bunch of perfect squares all squared. Only way you get zero energy, supersymmetric state, is if each dA is 0. Okay? The U1 analog of this problem would have been mod phi I squared, mod EI mod phi I squared sum over I is 0. So you see from the U1 analog that if you had one field of charge E and one field of charge minus E, it's very easy to get 0. Just make phi equals phi tilde. Okay, it's something very similar will work. Okay, any other questions or comments? Let me quickly just tell you where we're headed. In this NF less than NC case that we've started studying, we will show that this theory in the absence of mass has no vacuum. So the theory is sort of sick. However, when we turn on a mass, the reason the theory is sick is that there is a potential which goes, starts this way and decays off to infinity. Never flattening out, just keeps going. But you see, a mass is something that gives you a confining potential. So if you add a mass, you can take that and the mass and get a vacuum somewhere. Okay? So by adding masses to this theory, we get sensible theories. Okay? And these sensible theories will often have, discrete vacua because the scalar fields are all massive. You see, the reason that this theory was not sensible was in the scalar sector. Scalar fields are very wishy-washy things. If you've got a massless scalar, there's always danger you have trouble. And in this case you did. But a massive scalar is much tighter. Okay? And so there you cure that. Once you made the scalar massive, the scalars don't matter so much anymore. And that's sort of what you wanted, right? It's sort of what you wanted because we were trying to imitate the physics of QCD, and QCD doesn't actually have scalars. Okay, so we will see genuine vacua in this theory when all fields have masses, and those genuine vacua will presumably capture the physics of this confining theory. Okay. Then what we will do is the following. Okay, what we will then do is to move beyond NF less than NC. We will see that this Affleck-Dine-Seiberg superpotential makes no sense then. In the cases with NF less than NC, there's no superpotential. And in fact, physics is actually very different. We will find evidence that in some range of parameters there's conformal dynamics. We will find evidence of electromagnetic duality, dual descriptions of the physics, and quite wonderful stuff. We'll take maybe 2 lectures more to complete this discussion.
Adding mass will preserve the U1R class.
Adding mass preserves, adding mass breaks all symmetries, yet we will be able to analyze it.
Still we will be able to this.
Still we'll be able to analyze it. The reason we'll be able to analyze it is this, that we will give an argument that when you add the mass, the full superpotential is the sum of the classical superpotential that we added plus this superpotential. And the argument goes somewhat like this. Anyway, maybe we should see the argument, but let me tell you in words. The argument goes somewhat like this. If the mass was upgraded to a background chiral field, okay, then if we allow the mass to have its own transformations, then the full superpotential should remain invariant under A, transforming the fields and also transforming the mass. Okay? So then we'll basically write down the most general thing we can do, right, including also the mass, and then use various physics arguments to constrain various limits, to argue that the only thing we can add is the sum of these two. You'll see how that goes. You'll see how that goes.
You are saying some like symmetry breaking term kind of?
Exactly.
Where phi.
Exactly. So every time a term in a Lagrangian breaks a symmetry, we can restore symmetry if we allow ourselves to transform that term in the Lagrangian. Right? The novelty here is that we will think of this mass also as a chiral superfield. So you see, the point is that we will not, because of that, you won't be able to add m star. Okay? You'll see how it goes. Okay, any other questions or comments? Okay, great.